So, and inverse functions are the opposite. Ladies and gentlemen, I guess just gentlemen now. What does the opposite only mean in mathematics? Nope. Only one type of inverse is an opposite. Additive. What is the opposite of 7? Negative 7. What is the opposite of negative 13? Positive 13. Opposite only means the additive inverse. So we need to be careful about that. We do use inverse operations to create zeros and ones. Okay, so x becomes the output and y becomes the input. Remember, and that's referring to this idea, right here, y equals f of x. What's the input if we have y equals f of x? X. And the output is, hey guys, go ahead and pause at this point. We clearly have things that we got to learn. Input is x, output is y. What would be the function notation for the inverse of this function?
X.
So, typically we don't use f of y, we use g of y. Remember, what was the input became the output, and what was the output became the input. Yes, sir?
Why don't we change it up to G?
So, typically, if I define f of x as 3x minus 7, g of y, or f of y, that would be the same exact function, except y would be the input, right? So that actually doesn't give me the inverse function. That just has y as the input. For the inverse, we need a truly different function, right? So the f and the g are defining what the function is. What's on the inside just tells me what the input is. Does that make sense? What did that say, Keyshawn?
No, I was about to say what I was typing. I was like, I don't know.
Okay, so I will point out,
I'm still.
if you have y equals x squared as a function, what's the inverse of that function? Okay, the inverse operation is a square root, but what's the inverse function?
G equals.
G equals?
Right.
Well, I already have y equals. Remember, what is the output becomes the
X.
input, right? Square root of what?
X.
Y.
Y squared.
X.
No.
Oh.
Square root of y is equal to x, right? What was the output becomes the input. What was the input becomes the output. And so notice these would be inverse functions. Remember, you could say f of x equals that, or you could have said g of y is equal to that, right? Those are all different notations for that. So what about if I gave you y equals the natural log of x? What would be the inverse of that function?
That's Y equals.
Y.
Remember,
This is not some opposite natural.
it's the inverse of a natural log, but what is the inverse of a natural log?
It'd be E equals YX.
Not e equals,
Y.
remember, what's my output now?
E
X.
Equals E.
Y'all, I've heard y'all say e, and Xavier, you were the first one to even say the e, but we're missing something about that. E raised to the,
Natural log. No.
raised to y. Remember, what was the output becomes the input. Remember, I'm just asking what's the inverse function. You're starting to try to compose them, or maybe what we did to get that inverse. I'm just saying, hey, if y is equal to the natural log of x, what's the inverse? Well, x equals e to the y, right? The inverse of a logarithm is an exponential. The inverse of an exponential is a logarithm, right? So that's a big part of it. Another thing that we need to remember then is this. Graphically, what is happening? This is an important detail that no one mentioned. It's a reflection across what line? There we go. Remember, it's a reflection across y equals x. And so we already know, right? An exponential function, especially an exponential growth, looks something like that, right? So if I reflect, even though you don't know what a natural log function is yet, anybody want to come up here and give me a sketch of what the natural log function might look like? Just make a guess, come on. So we just need to make a prediction. We don't have to get it right, we'll discuss it.
About make this big here.
Okay? So what do y'all think about that? That look kind of like a reflection across that line y equals x? The one thing I'll point out is, notice how this right now is approaching the x-axis? So what is this supposed to approach?
Y.
The y-axis, right? That look like a pretty good reflection now? One thing I'll point out is this right here as well. Anybody know what I get if I substitute a 0 in? E to the 0 would be what output?
Zero.
What's anything raised to the 0 power?
Oh,
We talked about that recently. Anybody want to guess what this point over here for the inverse function would then be? 1 comma 0. Notice what happens to the inputs and the outputs. They switch. Because we're reflecting across that line y equals x, everything about the x and the y switch, right? And so we'll go into more detail about that later, but that's an important thing to note about inverse functions, as they are that reflection across y equals x. The last and important detail is this. If functions are inverses, what would f of g of x equal? I guess technically we usually use g of y. What would f of g of y equal?
X.
Not x.
Y.
So remember the input here is that y, so it would end up equaling just y. Now if I were to look at g of f of x, what would that equal?
X.
That would be the x. Remember how everything is going to cancel out when we compose those two functions if they are inverses, right? Now, I do want to contrast that, and I'm probably going to develop a small homework or practice set so that you get some practice with this. Let's say f of x equals 1 divided by x, and let's say that g of x is equal to, actually let's do 7. And g of x is equal to x squared. First off, could those be inverse functions? What's the inverse of a square? Square root, right? So those aren't inverses, but could I still compose them, right? Yeah. What do you think f of g of x might equal? You say 7 divided by x? But that's what f of x was.
X over 7.
So x divided by 7? Or maybe 7 divided by x squared?
No, x squared divided by 7.
Okay, why x squared divided by 7? Well, we need to be careful. It's not that g of x comes first. G of x is actually the what? It's the input. So what's the main function we're looking at? F. Remember, g of x is the input, f is the output. So technically 7 divided by my input is g of x. But what is my g of x? What is that equal to? That would be f of g of x. In a similar way, I could do g of f of x. Now what's the input? F of x, and the output is g. So I'm going to have something being squared. Specifically, the input is f of x. So 7 divided by x. Is that correct? Look again. There's a small error.
Oh,
whatever.
parentheses. Alright, 7 x.
Well, 7 divided by x. Right? Earlier I was just squaring 7. But notice that's all a composition of functions is substituting those inputs in.
So the input gotta go first in the equation, then, well, the main thing we're looking at gotta go first.
Well, and if you just think about it, it's g of this thing, that's my input.
Mhm.
And you can even do that with numbers, right? G of f of 8, right? Notice I would do f of x squared, so it'd be 7 divided by x squared, so that would be, see how the 8's in the place of 7? So there should be 7 divided by 8 squared, right? So my main function is g, I'm substituting f of x in, and then I substitute 8 in for x. So you can actually figure out values that way as well. Okay. Obviously I'm not testing on that, it's just something to be aware of.
Are
to
you
help.
not testing this on
I'm not testing you
the
on
number?
compositions with numbers like that, yeah. But like, you will have to compose functions to determine if they're inverses or not. So only if it composes to here will it be an inverse. If it doesn't compose to there, they're not inverses. Does that make sense? So you'll have to be aware of that. Okay, so let's get started with today's actual lesson. We're gonna wrap up lesson 4. What is an inverse function? There's just a couple of small details we need to look at that. And then we're gonna just briefly touch on lesson 5, using models to answer questions, before we look at the textbook or printout for some of us. Thank you, sir. Printout for the lesson on the Caleb, what number? 12? Okay. I'm going to remind me to get back the understanding checks at the end of class. Your homework, one of your homework assignments literally is just to look over your understanding check and devise a question that you want to ask before tomorrow. So I'll give you a blank copy so you can look to see what you need to ask the question about. Okay. So objectives with this lesson 4 that we've been on. I can explain how two functions are related graphically when they are inverses. How are they related graphically when they're inverses?
What's that?
How are two functions related graphically when they are inverses? They reflect reflections across y equals x. All of the x and y values are going to switch. Right? They're transposed is that mathematical term. They switch places. And then I can compose two functions algebraically to determine if they are inverses of each other, and we talked through that briefly. I believe we finished all the way through D in this class, did we not? Do we have information written on D through D?
Yes.
Look at the task 2 questions. No, yeah, you got through D. Maybe we didn't quite finish, so let's look at that together, I guess. Yeah, someone already mentioned, Mr. Kinney, you need to get more space for that. It's a detail of that task that I will have to update for sure in the future. I should have flipped the amount of space for D and E, but here we are. So you should use your own function. I'm going to use Caleb's square root of y hat equals 0.33x minus something. Square root of y, or yeah, square root of y hat equals 0.33x minus 0.28, okay? So first off, I want to point out and ask, is that the model for the original data set, the inverse function, or something else?
That's the original. No, that's not the original.
That's transformed.
Remember, that's the transformed linear. Remember, see right here where it's linear, right? And there is the transformation on y hat. So what is the model for Caleb for his model for the original data?
All that raised to E. Or E.
Y hat equals,
So remember, we need the inverse of what's there. I don't have a logarithm.
yeah, you put that square root and you square it.
Right.
Instead of-
I have a square root, so I need both sides to be squared. And one thing I will point out is, because I've heard several students already today, and I think I heard this on Friday as well, they're like, oh, use the inverse. Well, it doesn't matter which equation we're trying to get, we're going to use an inverse. You've got to remember, if I want the original model, then I want f of x equal to y, right? And I'm actually going to go ahead and take off the hat, because we're focusing on the idea of inverses, not models. But f of x equals the y. So if I want the inverse, we got to remember I want g of y, which is equal to x, right? So what would it be for Caleb for us to get there? Caleb, what did you get? I guess is a better question for that inverse function.
I don't think I did.
You had to.
No, I don't think I did.
What you talking
It'd be under c, dude.
You see?
Yep.
Oh, right here.
X equals g of y.
Oh yeah, equals, parentheses, y squared.
square root.
Square root
Yeah.
of y.
Plus 0.28 divided by, times 1 divided by 0.33.
Times that reciprocal. So we talked about this last week, where like every operation is the inverse and it's in the inverse order, right? So we have these two functions, and if they are inverses, when we compose them, we should get just the variable with nothing else. So again, so I'm gonna go through this one, f of g of y with y'all. You can write this down on a separate sheet of paper or on the back. You should have plenty of space on the back, I believe, if you want to. Yeah, there's nothing there. So f of g of y, what's the main function, and then what's the input for that main function?
F is the main function.
F is the main function. So I'm looking at 0.33. What's gonna be in the place of x? Remember, my input is now g of y. Can you skip that step of putting g of y right there and go ahead and put this in? 100%. It's your choice. I like to do that to make sure it's clear. And then substitute it in afterwards, because notice, none of that green is going to change. The only thing is, what's going to get substituted in for g of y?
Six.
Square.
You said what's gonna be what?
What's going to take the place of g of y?
The equation.
Oh, square root of y, I mean, yeah, square root of y.
All of that, right?
Oh.
Literally, g of y, which was equal to x, is equal to all of this. So all of that's going to take the place, and that's what we want to keep in mind.
Square root of y.
Yeah. And so we gotta be careful with our parentheses. And if you want, like, you have colored pencils on your desk, you can use them to help you keep track of those different details. So what do we want to note would cancel first? Or does anything cancel first?
Yeah.
Isn't that squared the absolute last operation there?
Yeah. But the plus, hold on. No. Never mind.
So we got to pay attention to the order of operations here. The square is the absolute last thing that's being applied, so it can't cancel that square root that's in the very center.
I mean, order operation, it's going to come first.
But what comes before exponents and anything inside of parentheses? Isn't all of this inside of parentheses?
We're gonna do it like that then.
It's not do it like that. That's how you follow the order of operations. Okay. So what does anything cancel first?
The 0.2.
But notice that 0.28 is inside of those parentheses as well. So I can't do that
Oh,
0.2.
33.
And so that's what we want to notice is like what is in parentheses and then what is separated from each other. And it might look like those don't go together, but we're multiplying all the way through, right? So really what you could do is switch the order here, which might make it easier to see. But when you multiply, the order can be switched. So you could rewrite that as 1 divided by 0.33 times square root of y plus 0.28. Now it's very clear with 0.33 divided by 0.33. So I've got parentheses square root of y plus 0.28. Notice I dropped off these blue sets of parentheses because what's 1 times anything? Just that thing, not 1. It's itself, right? So there's that minus the 0.28 squared. It's not get rid of, they add to give me 0, right? I'm using the fact that they are additive inverses. Square root of y squared.
So it cancels out. So
The square and the square root would now cancel out. But the order matters. You can't just magically say, oh, I know the square and the square root are going to eventually cancel out, because then you're skipping important steps, right? But mathematically that works.
That's just checking, order,
It's gonna be on the test. Right?
Say it again.
we're already trying to equate this is.
Well, it's not just checking our work. I'm asking you to prove that they're inverses. And on a test, and yes, it will be on a test, on a test, I may just give you two functions and ask, are they inverses? Right?
Are we able to do that?
And so you would have to do that composition algebraically to determine if they're inverses. Like we did that just a second ago, right? We logically said, okay, those can't be inverses, right? However, we tested it as well when we looked at f of g of x. Did those simplify to give me just an x or just a y? No. So they're not inverses, right? That's how you would mathematically prove that, Xavier. Okay? And so yes, stuff like that would be on the test. Okay.
We'll have the, it's gonna be in that same format?
Well, I would probably just, hey, here's these two functions, are they inverses? I will create some practice problems because I know we probably need that, where I am in the process of creating some practice problems because I know we need that, where you would see it like that. But this is the concept behind it, okay? Not what I wanted. So here when you look at E, graph the result from the composition of g of f of x in the same window as the model and its inverse. And we briefly touched on this on Friday? No, because we're on Monday right now. What's it I just said? Oh, there we go. So this is from a previous class. That's fine. Square root of x minus, what was your 0 point? So plus 0.28, right?
Not minus.
Not for the inverse.
Oh, for the inverse.
Yeah, this class had a slightly different thing, which is more than fine. So I want you to notice, right? We have two different functions here. We have that red square root function and the blue quadratic function. If I were to reflect that quadratic across the line y equals x, do I get just that red square root function? I do not. If I were to reflect this blue quadratic function across y equals x, what should that function look like? Or what should the reflection look like? Is it going to stop here? What's it going to do?
Don't touch it.
So it's going to give me a horizontal parabola, right? That's definitely not what it looks like. So there's a couple of things I want you to make a note of under E. First things first, to understand why that doesn't happen, we need to know what a function is. A function is a relation, which all a relation is any kind of combination of inputs and outputs, okay? But a function is a relation where each input maps to one and only one output. And that's the proper definition. I'll explain what that means in just a second.
I was going there, though.
No, they're in PE.
No,
I
no,
know.
no, no.
Yes, they are.
Let me check.
I mean, I have checked because, like, who in the world is just quitting class?
Oh, that's just really cool.
I looked it up, and the student that I knew that was out there is in PE at that time. I was like, got it. Okay, so I want y'all to look here. For this x value of -3, how many outputs does that have on the blue quadratic function? It just has one at a y value of 1.5. Okay? So what about if the x value is 1? What does it look like the output is? It's about 0, but how many outputs is that?
One out.
Just one output. If you look over here at an x value of 4, how many outputs?
One out.
One output. So that quadratic is a function. Each input maps to one and only one output, right? Now, if I ignore this bottom half of this, when I look at an x value of 1, what does this square root function have? How many outputs?
2. No.
Just one, right? And I do want to point this out. Remember how here we said it was 4, 1? What's this point?
1,4.
Oh yeah, because the x and the y switch, right? But I want you to notice, if I include the bottom half of this parabola, right? Now when I look at this x value of 1, it has one output here, and there'd be another output here. Would that be a function? Right? If I look over here at an x value of, let's say 3, see how it has an output up here? And it would have an output down here, is that a function? No. And the reason why we only get 1/2 is, well, one thing I'll point out is, whenever we take a square root, how many solutions are we supposed to get? So like in the truest sense, when I solve for x, I should have had a plus or a minus. And so if I actually take this function, I put it in here and I put the minus or negative. Notice how that does create the other half of that parabola, but is it now a function? No. And so what we have to do is figure out a way to still get a function, because, well, we need an inverse of a quadratic, okay? So here's what we have to do. First off, we get on a function as a relation where each input maps to one and only one output, okay? Well, to get an inverse function, so to get, different color, and this would also go under E. The original must be 1, 2, 1. That is actually a term on the Big Idea graphic organizer, so pay attention to that. So to get an inverse function, the original must be 1 to 1. What we mean by that is, not only does each input map to one output, but also each output maps to, any guesses how many inputs? One input. Super logical, right? 1 to 1. We'll talk about why we need that in a second. This would also go under E. Okay. Take your story. So I want y'all to notice these 2 points here. What would be the coordinates roughly of this point? But not exact, but roughly. Say again? Not -1. Not 2, 1. -2, comma. It's going up. It's a positive 1, right? To the left 2, up 1. Guys, we gotta be careful about those positives and negatives. What would this point be? 4, comma 1. So remember, that's for the original function. When I look at the inverse function, those x and y values are going to switch. So for the inverse function, this point would be
Negative
1, -2.
1.
1, -2. Remember, the x and the y just switch places. This one would have, notice this one input of 1. How many outputs does it have? This input of 1 has an output of, and that same one has an output of, so how many outputs does it have?
No, 2.
2.
Because
It's 2 different guys, it's 2 different numbers, right? We good with that idea? Yes?
Yep.
Actually, yes.
So that means it's not.
Well, once we get the inverse with those 2 points, yeah, it would no longer be a function. Notice that's this part of the curve, right? Where it comes down here.
So it's kind of like how many times that one you see.
But if they're -2,
It's just like it's
and
working
that
out.
4 and that 1 with all the 1, then it would be a function.
No, because still, even if those were the only 2 points on the original function, if I get the inverse, right, I switch the x and the y, I would still get 1, negative 2, and 1, comma 4. Just that, those 2 points prevent it from being, and remember, it has to be 1 to 1 is the idea. Because notice, each input already has one output, but this one output has how many inputs?
So,
2. That's why it's not an inverse function, which is why, or it's not a 1 to 1 function, which is why when you reflect that parabola, right, you would get something that's not a function, okay? So that's showing that it's not 1 to 1, which is why you can't just reflect it. So I will never actually be able to get an inverse function for this entire parabola. However, if I could mark off part of this parabola, how could I do that so that I do have a 1 to 1 function?
turn off your x.
Say that one more time.
Straight under one.
Can you show me what you're talking about? So let's look at what Caleb was discussing or thinking here.
You said split it in half.
Alright, so do y'all think that that would split the quadratic in half?
No.
Yes.
It's close, but I would,
Because the x equals 1.
why do you say x equals 1?
Cause that's when it turns to the x.
It's not just that,
And then it goes back up.
it's close to x equals
That's not
1,
the,
but there's another more important point that we should be thinking about.
That's not the,
Say that again?
that's not, rotate of the parabola.
Oh, isn't there symmetry around the what? The vertex, right? So not here necessarily, but, and I agree it's about the x equals 1, I would probably mark it here, but Preston, it's not because that's where it touches the x-axis, it's because that's where the vertex is, and there's symmetry around it, right?
Yeah.
Notice, if I take out all of this, is it now, well, is it 1 to 1?
Yeah.
And I want you to notice, if I reflect all of these points, do I get this red square root function? Notice this point becomes this point. This point right here becomes this point right there. See how the x and y values are switching there? This point becomes this one.
So we want to split quadratic function that has inverse with 1 and 1.
Well, what we would have to do, and so this is where the last detail that we're going to add on to here is, if the function is not,
What is going?
still under E if you have the room, if not, put it on the back side. So if the function is not 1 to 1, we have to restrict the domain.